Welcome back. In this video, we're going to explore the principles of hydrostatic pressure, including Pascal's principle and Archimedes' principle. But before we dive into those concepts, let's first understand what pressure really is. Pressure is defined as the force applied per unit area. Now, how does this apply to liquids? If you consider any point within a liquid, the pressure at that point depends on the depth of the liquid above it. More precisely, the pressure is caused by the weight of the liquid column above that point, acting on a unit area. This pressure increases with depth, because there's more liquid pressing down from above. Let's consider a point located h meters deep in a liquid, with a surrounding cross-sectional area A. The pressure at this point is given by the weight of the liquid column above it, divided by the area A, which is measured in square meters. The weight of the liquid column is determined by its volume, which is the cross-sectional area A, multiplied by the height h. This volume is then multiplied by the density ρ and gravitational acceleration g to give the weight. This represents the force exerted on the area A. To find the pressure, defined as force per unit area, we divide this force by the same area A. This leads to the expression for pressure at a depth h in the liquid. Pressure is a scalar quantity. It has magnitude but no specific direction. In the context of fluids, pressure at a point refers to the force exerted per unit area at that point, and it acts equally in all directions. When considering a point inside a liquid at a certain depth, the pressure depends only on the depth, the density of the liquid, and the acceleration due to gravity. It is independent of the shape or size of the container. Pressure is measured in units of newtons per square meter, which is also known as the Pascal. Now, what about the surface of the liquid, that part exposed to the atmosphere? Wouldn't the atmosphere itself exert pressure on the liquid? Yes, absolutely. That's what we call atmospheric pressure. So, if we're looking at a point P deep inside the liquid, the pressure there isn't just from the liquid above it. It's actually the sum of two pressures, the atmospheric pressure pushing down on the surface and the pressure from the weight of the liquid column above point P. Together, these give us what's called the absolute pressure at that point. We can express it like this. The pressure exerted only by the column of liquid is known as the gauge pressure. So when we talk about absolute pressure, we're referring to the total pressure at a point in the liquid, which includes both the atmospheric pressure and the gauge pressure. In simple terms, absolute pressure equals atmospheric pressure plus gauge pressure. This distinction is important, especially when using pressure measuring instruments, because many of them measure gauge pressure rather than absolute pressure. All right, let's attempt to solve this question. We have a U-tube containing two different liquids in static equilibrium. In the right arm, there's water with a known density of 1,000 kilograms per cubic meter. In the left arm, we have oil, but its density is unknown. Now, we're told that the height of the water column above the interface is 135 millimeters, and the height of the oil column is 147 millimeters. Our task is to find the density of the oil. Now, how do we approach this problem? In the previous section, we discussed a key principle. At the same depth in a connected fluid system, the pressure is the same regardless of the shape of the container. That's precisely what we're going to apply here. But wait, does this principle of equal pressure at the same height still apply here? Not quite, and here's why. Earlier, we said that pressure is equal at the same horizontal level in a fluid, but that only holds when it's the same liquid and the system is in static equilibrium. In this case, we have two different liquids, oil on one side and water on the other. So we can't directly say the pressures at the same height in both arms are equal just because they're at the same level. But here's what we can say. At the interface, the point where the two liquids meet, the system is in static equilibrium. That means no fluid is moving, and the pressures at the interface from both sides must be equal. Why does static equilibrium matter? Because if the fluid were moving, the pressure at the same height wouldn't necessarily be equal. That falls under a different topic in fluid dynamics, which is governed by principles like Bernoulli's equation. But in our case, since the fluid is at rest, we can confidently say this. The pressure exerted by the column of oil above the interface is equal to the pressure exerted by the column of water above it. And that's the key to solving this problem. We can express the pressure exerted by the column of oil at the interface using its height, density, and gravitational acceleration. The same approach applies to the water column on the other side. The pressure at the point that lies at the same level as the interface is found by multiplying the density of water by gravitational acceleration and the height of the water column above that point. Now, because the pressures along the horizontal line through the interface must be equal, we can set the two pressure expressions equal to each other. Now we simply solve for the density of the oil by rearranging the equation. This gives the density of the oil as 918 kilograms per cubic meter. In the next video, we'll look at more examples like this. But for now, let's turn our attention to understanding Pascal's principle. Let us consider a setup as shown here. The cylinder is filled with an incompressible fluid and has a cross-sectional area A. Point P lies inside the fluid at a depth h from the top. The density of the liquid is represented by ρ. Let's work out the pressure at point P. Based on what we discussed earlier, the total pressure at point P is a combination of three things. First, the atmospheric pressure acting on the fluid. Second, the pressure due to the weight of the liquid column above point P. And third, the pressure exerted by the piston setup. Now, suppose we increase the pressure at point P by applying an additional force F on the piston. In that case, the total pressure at point P would now include one more contribution, the pressure resulting from that applied force. So how do we calculate that? We know that pressure is equal to force divided by the area over which it is applied. Since the piston applies a force F on the fluid surface and the cross-sectional area of the cylinder is A, the additional pressure introduced by this force is F divided by A. Now, to find the pressure difference caused by this additional force, we subtract the original pressure expression from the new one that includes the applied force. What we see is that the resulting pressure difference does not depend on the depth. And that's exactly what Pascal's principle tells us. According to Pascal's principle, any change in pressure applied to an enclosed fluid is transmitted undiminished throughout the fluid and to the walls of its container. In other words, the change in pressure caused by the applied force is felt equally at every point within the liquid, regardless of depth or position. Let's take a look at this problem. A piston with a cross-sectional area, A', is used in a hydraulic press to apply a small force, F', on the enclosed liquid. This liquid is connected through a pipe to a second piston with a larger cross-sectional area A. We need to find the force F that the larger piston can sustain without moving. Then, we'll consider a specific case. If the diameters of the pistons are 3.8 centimeters and 53 centimeters, what force must we apply on the smaller piston to balance a 20 kilonewton force acting on the larger piston? Pascal's principle tells us that any change in pressure applied to a fluid is transmitted equally throughout the entire fluid, no matter how deep or shallow the point is. So, if we look at the small cylinder, the pressure difference there, which we can call delta P, is simply the force F' divided by the cross-sectional area, A'. Since the pressure difference stays the same everywhere in the liquid, the large cylinder must also have the same delta P. For the large cylinder, we can express it as the force F divided by its cross-sectional area, A. We can now set these two expressions equal to each other to find the force F that the large piston can support without moving. Before we move on, let's think about what happens if the system isn't perfectly balanced. Imagine the smaller piston is pushed down by a distance d'. Because the liquid is incompressible, this pushes the same volume of liquid to the other side, causing the larger piston to rise by a distance d. Since the volume of liquid moved is the same on both sides, we can now relate the motion of the pistons using their cross-sectional areas and the distances they move. We can rearrange this equation to find how much the larger piston moves. This tells us that the movement of the larger piston depends on the ratio of the areas and how far the smaller piston is pushed. So if the input piston has a much smaller area, a small push on that side can cause a much smaller movement on the larger piston, but it can lift a heavier load. The work done by the output piston is simply the force it applies multiplied by the distance it moves. Using the relationships we just discussed for force and displacement, we can express this in terms of the input piston as well. What we find is that the work done by the output piston is equal to the work done by the input piston. This perfectly aligns with the principle of conservation of energy. No energy is lost or gained, just transferred through the fluid. Okay, let's return to our question. To find the force that must be applied to the smaller piston to balance a 20 kilonewton load on the larger piston, we'll use Pascal's principle. But first, we need the cross-sectional areas of both pistons. Since the area of a circle is based on its diameter, we can express each area using the formula pi times diameter squared divided by 4. We substitute these into our pressure equation, and after simplifying, we get a clean expression that relates the two forces through the ratio of their diameters squared. This final expression tells us exactly how much force is needed on the smaller piston to keep the system in balance. Now we can substitute the given values to calculate the exact force needed on the small piston to keep the system in balance. What we learned from this example is that a much heavier load applied to a large area cylinder can be balanced by a much smaller force applied to a cylinder with a much smaller area. With that, we have covered two important principles related to fluids at rest. Now let us move on to the third and final concept in the mechanics of static fluids, which is Archimedes' principle. Before we continue, I'd like to kindly ask you to give this video a thumbs up, subscribe to the channel, and hit the notification bell so you don't miss any updates. Your support truly means a lot. Thank you. Now, let's get back to the video. Let's try to understand Archimedes' principle with a simple setup. Imagine a solid sphere hanging from a weighing scale. At first, the scale shows the full weight of the sphere, which is just the pull of gravity. Now, if we gently lower the sphere into a container of water, we'll notice that the reading on the scale starts to drop until the sphere is fully immersed in water. Once fully submerged, the reading on the scale stays constant, no matter how much deeper the sphere is placed in the water. So, what exactly is happening here, and how does it relate to Archimedes' principle? Let's explore that next. To understand the physics behind what we just observed, let's consider a cylinder fully submerged in a pool of water. When an object is completely submerged in a liquid, we notice that there is a constant upward force acting on it, opposing its weight. This upward force is known as the buoyant force, and interestingly, it does not change with depth as long as the object remains fully submerged. In this section, we are going to explore what this buoyant force is, where it comes from, and how to calculate it. The cylinder shown submerged in water has a height of h and a cross-sectional area A. The top surface of the cylinder lies at a depth of h sub 0 below the water surface. The water has a density ρ sub 0. The mass of the cylinder is m, so its weight can be expressed as mg, where g is the acceleration due to gravity. We are assuming that the cylinder is in static equilibrium, meaning the downward force due to the cylinder's weight is exactly balanced by the upward buoyant force from the water. To figure out the buoyant force, let's first look at all the forces acting on the submerged cylinder. We'll start with the force on the top surface. This comes from the water pressure above it. The deeper the surface is, the greater the pressure. So to find this pressure, we multiply the liquid's density by gravitational acceleration and the depth of the top surface, which we'll call h0. Then, we multiply that pressure by the area of the top surface to get the total force acting downwards at the top. Now let's look at the force acting on the bottom of the cylinder. Just like before, we find it by multiplying the pressure at that depth by the area of the surface. To figure out how deep the bottom is, we add the depth to the top of the cylinder, that's h0, and the height of the cylinder itself. Since the bottom is further down in the liquid, the pressure there is higher. And because pressure is higher, the upward force on the bottom surface is also stronger. In the end, the buoyant force comes from the difference between the upward force on the bottom of the cylinder and the downward force on the top. When you work through the maths, it simplifies to a neat result. The buoyant force is equal to the fluid's density multiplied by gravity and the volume of the cylinder. This is the principle Archimedes discovered. The buoyant force acting on an object is equal to the weight of the fluid it displaces. Now, what about the pressure from the air pressing down on the surface of the liquid? It turns out this doesn't affect the buoyant force. That's because the air pressure pushes equally on both the top and bottom of the object. When we work out the difference between those two forces to find the buoyant force, the air pressure cancels itself out. Hold on, what about the pressure acting on the sides of the cylinder? Well, those forces are balanced. The pressure pushing in from one side is matched by an equal pressure from the other side. Because they cancel each other out, they don't contribute to the net force. So overall, the side forces have no effect on the buoyant force. Let us make this idea clearer with an example. What you see on the screen is a wooden block floating in a liquid. Initially, only 1/5 of the block is submerged. Then we add a 12 kilograms weight on top, and the block sinks further. It eventually settles and floats steadily when 3/5 of its volume is underwater. So what we want to figure out is how much the block itself weighs. Let's assume the volume of the wooden block is V, its mass is m, and the density of the liquid is ρ. Before the weight is placed on the block, 1/5 of its volume is submerged. This tells us that the buoyant force, which comes from the liquid displaced by the submerged part of the block, is balancing the weight of the block. Using this condition of equilibrium, we can now write an expression that relates the block's weight to the buoyant force. Next, let us consider the situation when a 12 kilograms weight is placed on top of the wooden block. This additional load causes the block to sink deeper into the liquid, submerging 3/5 of its volume. At this point, the buoyant force must balance the total weight, which is the weight of the wooden block together with the 12 kilograms mass. This new equilibrium allows us to write a second expression, where the upward buoyant force equals the total downward weight. The increased submersion corresponds to a greater volume of displaced liquid, which determines the new buoyant force. To find the mass of the wooden block, we take the two equations we derived and divide the second by the first. This step helps eliminate several common terms, simplifying the expression. What we're left with is an equation that contains only the mass of the wooden block, making it easy to solve. Solving this gives us the mass of the block, which turns out to be 6 kilograms. That brings us to the end of this video. I hope everything we covered was clear and helpful. I'll be sharing more examples on this topic in the upcoming videos, so stay connected by hitting the subscribe button and tapping the bell icon to stay notified. Your support and comments truly mean a lot. Thank you. Until we meet again in another video, take care and goodbye.